Hello everyone, welcome to another video lecture on vector space. In this video lecture, we shall study about the basis. So what is mean by basis? So let us first define a basis. For this we'll consider a vector space. So let V is any vector space. V is any vector space. And we'll consider set S, which is a subset of vector space V. S, which is a subset of vector space V. Then S is called a basis of V. S is called basis of V if it satisfies two conditions. First, S is linearly independent. First of all, S must be linearly independent. And the second condition is S spans V. So we have talked about these two concepts in the previous video lecture. You may find the link of these two concepts in the description list. So let us study how to find a basis. So for this, what we do? For this, we'll need to check whether set is linearly independent or not, and then set S spans V or not. So the very common example of a basis is the set containing S is equal to, say for example, 1 0 and 0 1. The set containing 1 0 and 0 1 is a basis of R square, and this basis is called standard basis. This is called standard basis of R square. Now let us check how it is basis. So first we need to check whether it is linearly independent or not. So to check S is linearly independent or not. So for this what we do? So first of all we will form the vector equation. So let alpha 1 v1 plus alpha 2 v2 equal to 0. So this implies alpha 1 v1 is 1 0, first element of the set, and v2 is 0 1, equal to what it will be? 0 0. Now this gives us alpha 1 and then alpha 2 equal to 0 0. So on equating, we will get directly alpha 1 0 and alpha 2 0. So as both the scalar in this vector equations are 0, that's why S is linearly independent. Now let us check whether S spans V or not. What is mean by S spans V or not? S spans V means if you take any element, any arbitrary element of R square, then that can be written as a linear combination of vectors in S. That is what is called as S spans V. So if we take, say for example, any arbitrary element, let any arbitrary element, or we generally use the word vector, in R2 we say xy. So we can write this xy as a linear combination of elements in S. Elements in S are V1, V2. Now here we wish to find out the value of x and y. So what you will get? You will find that x is nothing but alpha 1 is nothing but x, and alpha 2 is nothing but y. So as the value of these two scalars exist is sufficient to show that the xy is written as scalar combination of elements in S. So this implies S spans V. So as both the conditions are satisfied, therefore the set the set S containing 1 0 and 0 1 is a basis of R square. Usually we denote this element 1 0 and 0 1 which are standard basis element by E1 and E2. So if I write E1, it means it's 1 0 in R2. E2 means 0 1. Similarly, if we wish to write the standard basis of R cube, so what will be standard basis of R cube? So standard basis of R cube is the set S having the element E1, E2, E3. There will be three elements in the basis. What are the E1, E2, E3 here? Where E1 is 1 0 0 because its element of R3 should be in the form of 3 tuple. Then E2 is 0 1 0 and E3 is 0 0 1. So if I ask anyone what would be the standard basis of R is to n, then it will be nothing but set containing E1, E2 up to En is the standard basis of what? R is to n, where each E1, E2, E3 will be a n tuple of the form. So E1 will contain 1 in the first place, rest of the elements n minus n elements will be 0. In E2 at second place we have 1 and all other elements will be 0. Like this the standard basis is obtained. Now let us define the next terminology, that is finite dimension. So what is mean by finite dimensional? Finite dimensional. So finite dimensional means a vector space V, a vector space V is called finite dimensional. It is called finite dimensional if it has a basis containing finite number of elements. If it has a basis containing finite number of elements. Otherwise, it is called infinite dimensional. So if basis does not contain finite number of elements, then it is called infinite dimensional. Now let us define the dimension. What is mean by dimension? So the number of vectors in a basis, is called dimension of vector space V. Dimension of vector space V. So say for example, if we have V is a vector space and S is a basis for V. In particular, if our vector space is say R square, and what is its basis? Basis is nothing but set containing E1, E2. This is we know. It's a standard basis. So what is the dimension of V? So dimension of V is nothing but elements or number of vectors in a basis. So here we have how many vectors? 2 vectors. So that's why dimension of V will be 2. Now, what is the dimension of the vector space 0? So in the vector space 0 has no basis. Basis contains 0 elements. So that's why it's a 0. Whereas dimension of V is always n if it is of n dimensional. If the space is of n dimension, that is r raised to n. A vector space that has no basis, finite basis, is called infinite dimensional. Now, let us see some standard basis and their dimension for a given vector space. If we have a vector space and their standard basis are known, then the dimension can be obtained easily. So if suppose we have r square, right, two tuple space, so its standard basis is always e1, e2. So number of element in the basis is 2, that's why dimension is 2. Similarly, if I have r cube, so standard basis will be e1, e2, e3, where e1 is its 3 tuple or triplet, which is 1 0 0, like this. So number of elements in the basis is 3, e1, e2, e3, so 3. Similarly, if I have n space, so its basis contains e1, e2 up to en. So n element in the basis, that's why dimension is n. Similarly, if we have a matrix space of order m by n, if we have a matrix space of order m by n, then its basis will be nothing but a set of the form Eij, where I is greater than equal to and less than or equal to m, and j is between 1 to n. So in this case, the dimension is m into n. Now, so let us try to understand this in particular. So if I have 2 by 2 matrix space, 2 by 2 matrix space. So what are its basis elements? Standard basis elements. So they are nothing but E11, E12, E121 and E22. These are the standard basis. Where what are the elements of E11? Elements of E11 means it is of size 2 by 2, and at 1 position you will get 1. Rest of the elements 0. E22 means again it's a 2 by 2 matrix where 2 position is 1 and rest of the element is 0. So like this we have 4 elements in the basis. Hence the dimension as per this general formula would be m is 2, n is 2. So it will be 4 elements which are E11, E12, E21, E22. Now let us try to understand this with the help of another example. If say we have matrix space of size 2 by 3, then how many elements will be there in the basis? So in the basis we have 6 elements. What are these 6 elements? The 6 elements are E11, E12, E13, then E21, E22 and E23. These will be the 6 elements in the basis. Where what will be the E11 in the form of element, or say E21 we want to write. E21. So it is of size 2 by 3, means 2 rows and 3 columns. So except 2 1 position, all other elements will be 0. So it's 0 0 here. This is 2 1 position. So 1 here and remaining element 0. Like this you can write rest of the elements. I hope concept is clear to all. Now here 6 element in the basis, so dimension is 6. Now next vector space is polynomial space. Polynomial space, which we denote by Pn of x or Pn simply. So its standard basis has elements 1, x, x square, and x raised to n. So dimension, if you count them, so they comes out to be n plus 1. So that's why dimension is n plus 1. If I take only a polynomial space where degree is not mentioned, then the standard basis will involve element of the form 1x x square to infinity. So as infinite elements are there, so dimension will be infinity. So I hope this concept of forming the basis and deciding the dimension is clear to you all. Now let's have one example on deciding whether a given set is basis or not. So show that the set S is equal to say 1 1 1 minus 1 is a basis for R square. So solution. So here we need to show or prove two things. First one, to show S is linearly independent, and number 2, S spans the given vector space. What is given vector space? R square. So these two results we have to show here. Now, in order to show that a given set is not a basis, it's sufficient to show that one of the condition fails. Right? Either show that S is not linearly independent or show that S does not span R square, just to prove that given set is not a basis. So here in this case we have to show the result on a positive side, that's the basis. So both the condition must be satisfied. So let's go for first one. So to show S is linearly independent, we shall start with a vector equation. So let alpha 1 v1 plus alpha 2 v2 equal to 0. Obviously, what is v1? Elements of vector this set S we denote by v1 v2. So this is v1, this is v2. Substituting v1 v2, so alpha 1 1 1 plus alpha 2 1 minus 1 equal to 0 0. Simplifying as per our usual method. So first element multiply with the first element and then add them. So it's alpha 1 plus alpha 2 equal to 0. Second equation will be alpha 1 minus alpha 2 equal to 0. Done. Now I am having equation number A. Now to check whether it's linearly independent or not, once you get system of linear equation, what we do? We'll write this in a matrix form, which is Ax equal to 0, where determinant of A we will calculate. Determinant of A is how much? Coefficient of alpha 1 and alpha 2 in this equation. So that is 1 1 then 1 minus 1. Now this comes out to be minus 2, which is not equal to 0. So when we know that when determinant of A is not equal to 0, means the set is linearly independent. Hence, the first result is proved. Now let's prove the second one, that is S spans R2. So for this, we'll consider one arbitrary element. So let V is equal to, say, ordered pair XY belongs to R2, such that this V is a linear combination of V1 and V2. That is, V is alpha times V1 plus alpha 2 times V2. Now, recall here we have already worked for the simplification. So, what we see, what is the difference in equation 1 and equation 2? In equation 1, we have right hand side as 0, here 0. This linear combination is equal to 0. Whereas, in this equation 2, what we find, if you observe this equation 2, what we find, the right hand side is not 0, it's V. So this is the only difference. So if we simplify the way we have solved here, what we find here, I am having right hand side element as 0, 0, 0, 0. So in place of this 0, 0, we have the elements of V. So what it will be? So we can write it directly. What it will be? So I am having first equation as alpha 1 plus alpha 2 equal to 0. In place of 0, what do I write? I'll write first element of V, that is what? X. And it alpha 1 minus alpha 2 equal to what? Second element of the V, that is what? Y. Like this you can write down directly and save your time. So it's alpha 1 plus alpha 2 equal to X, and then alpha 1 minus alpha 2 is equal to Y. Done? Right? Now, after this, we know that what type of equation we are getting if I write this in the matrix form. So, we are getting Ax equal to B. We are getting Ax equal to B. And as per the result which we know, if we have non-homogeneous equation, that is, B is containing non-zero elements. In this case, if determinant of A is not equal to 0, then the system of equation, right, system of equation which I am denoting here by B, say, equation number B, right, then the system of equation always has a unique solution. And what is that unique solution? It says that alpha 1, alpha 2 exist. So since we have already seen in the previous part, determinant of A is minus 2, which is not equal to 0. Hence, the equation B has unique solution. This has unique solution. Therefore, it guarantees that alpha 1, alpha 2 exist. So, we just want whether alpha 2, alpha 1 exist or not. So, therefore, this implies that set S spans R2. So what we have shown? We have shown that S is linearly independent and also S is spans R square. So this 1 and 2 implies, equation Roman 1 and Roman 2 implies S is a basis for R square. So I hope the problem is clear to all. In the next video lecture, we shall see some interesting and little bit complicated examples in the next video lecture.